What if I told you we've now seen a galaxy from when the universe was barely out of the cosmic crib, not even 300 million years old? Today we're diving into how the James Webb Space Telescope pushed the cosmic dawn farther than ever, catching light from galaxies at a staggering redshift around 14. Picture this: a faint red smudge on a deep image that turns out to be a living postcard from the first sunrise of the cosmos. Wild, right? Meet JADES-GS-z14-0, the current record holder for most distant confirmed galaxy. It was discovered by JWST's JADES program using NIRCam to map the sky, then confirmed with NIR spectroscopy. The team measured a precise redshift of about 14.3, which puts this galaxy at roughly 290 million years after the Big Bang. That one number is a time machine stamp. The farther the redshift, the earlier the moment we're seeing. So what does Z14 actually mean? Think stretch. Because the universe expands, light gets pulled to longer wavelengths over billions of years. Hydrogen in intergalactic space leaves a sharp fingerprint called the Lyman alpha break at 121.6 nanometers in the rest frame. At Z14, that break slides to about 1.8 micrometers, deep in the infrared that NIR spec can read. You see a crisp cliff in the spectrum. That cliff is your cosmic timestamp. That is how astronomers pin the distance and the age of this tiny ancient galaxy with confidence. But here's the thing: this record isn't just a trophy. It tells us about Reionization, the era when the first stars and galaxies flooded space with ionizing photons that stripped electrons off neutral hydrogen. Early on, the universe was foggy to ultraviolet light. As more stars ignited, bubbles of clear space grew and merged until the fog lifted. Most lines of evidence suggest this great clearing was largely complete by redshift around 6, roughly a billion years after the Big Bang. JWST is now catching the very first sparks of that sunrise. And JWST keeps surprising us. Many early galaxies look brighter in the ultraviolet than models predicted. That could mean rapid star formation, top-heavy stellar populations, or simply that there are more of these galaxies than we expected. Spectroscopic confirmations like JADES-GS-z14-0 show this is not a fluke. Even more provocative, JWST has seen strong Li alpha emission as early as Z13 in at least one source, hinting at local ionized bubbles forming earlier than we thought. Cosmic dawn is not a uniform switch-on. It is a patchy, growing archipelago of light. If this is starting to make sense, hit subscribe for a new Science Reveal episode every week. Here's the step-by-step of how this works. Step 1. Survey with NIRCam. Astronomers take ridiculously deep pictures in several infrared filters. Galaxies at extreme redshift drop out of the bluest filters because the Lyman alpha break has moved beyond them. Step 2. Select. Candidates are picked by color patterns that scream very high redshift. Step 3. Confirm with NIR spec. JWST opens a microshutter array, takes spectra of many faint targets at once, and looks for that telltale break or specific lines. Step 4. Interpret. The measured redshift gives a look-back time, luminosity, and clues to star formation rates. JADES-GS-z14-0 passed this test with a clean, high-confidence spectrum. Bonus info. How big are these baby galaxies? We're talking compact, a fraction of the Milky Way's size, yet forming stars at a frantic pace. Measurements for the record setters put their sizes in the ballpark of a couple of thousand light-years, which is tiny but mighty, and more than enough to pump out UV light that carves those early ionized bubbles. Also, not every very distant candidate survives spectroscopy. JWST's power is that it can weed out imposters and lock in true distances. Finally, Reionization likely wrapped up by around Z6, but its internal story is messy, with different regions clearing at different times. That is exactly why spectra at Z10 are such gold. Let's land this. Today you met 3 big ideas: redshift as the ruler of cosmic distance and time, the Lyman alpha break as the spectral cliff that proves it, and Reionization as the universe's fog-to-clear transition powered by the first stars. JWST's JADES-GS-z14-0 shows that the dawn may have started earlier, brighter, and more unevenly than our models expected. Next time you see that tiny red speck in a JWST image, remember, it is not just a dot. It is a lighthouse from the first morning of everything. If this blew your mind, share it with a friend who loves a good origin story.